So the next thing is a special type of event called independent events. Independent event is any two events where you know they don't affect the outcome of the other. And either they will tell you that, or it should be fairly obvious that they're independent events. So either in the application it'll say they're independent, or again, like I said, it'll be fairly obvious that the two events are independent. If the two events are independent, then there's a special, again, type of way that we figure out the probability. It's kind of what we've been doing a little bit. This is, again, more formalizing what we've already been doing. All right, so an example of two events that are independent is you're short, your favorite color is blue. Right? The probability you're short and the probability your favorite color is blue have no effect. Being short and liking a color have no effect on each other, right? You work out 7 days a week, your blood pressure is pretty good. Now, those might have these, so this would be, I would say this would be independent. This would be dependent, but not always. Doesn't always come out. So again, that one could be dependent or independent. Depends on the body chemistry. If two events are independent, we can do the multiplication, which is what we've been doing when we have no repeats and stuff like that, right? Because the probabilities are the same. The first probability has no effect on the other probabilities. Now, where it matters is when I'm no longer allowing repeats, then they're dependent cases, right? If I pull out my M&M and I eat it, the second M&M pick has a different probability, so they were dependent on each other. Right? And so independent events would be more like the first outcome. When I replace it, the first probability is exactly the same as the second probability. Right. An example of two outcomes which one doesn't affect the other is I flip a coin and roll a die. What happens when I flip a coin has no effect on the chance of what happens on my dice, right? They're two completely separate events. And so we take the probability an experiment, we usually flip a coin and you get heads, the probability you get heads. And you roll a 2. Right? Getting heads and rolling a 2 are independent events. You just find the probability that you get heads and multiply it by the probability you rolled a 2. Write that out. Alright, so probability that you got heads, well, there was 1 out of 2, right? Probability of you getting heads is 1 outcome out of 2. Probability that you roll a 2 on the dice, well, there's only 1 2 on 6 possible outcomes for a dice, so 1 out of 6 was the probability you roll a 2. Multiply that out, that's 1 out of 12. The chance of rolling, you flip a coin and roll a dice, the chance of getting heads and the number 2 is 1/12. Alright, the next one's an application where they tell you. Alright, playing 2 games, and this is the ones that we tend to do a little bit more of. You play 2 unrelated games, meaning unrelated mean one game, whether you win or lose, has no effect on the other game, whether you win or lose. So they're independent events. The chance of winning the first game is 43%. The chance of winning the second game is 22%. Use the formula for independent events. Find the probability you win both games. Alright, so probability that you win the first and you win the second is just the probability that you win the first times the probability you win the second. Now, before I get started, when you multiply, the percents must be changed to decimals. You can't multiply percents, you can only multiply decimals or fractions. Must be changed to the decimal. Alright, so the probability of the first win was 43%, the decimal would be 0.43. The probability of the second win was 22%, the decimal would be 0.22. You cannot multiply 43 times 22. It doesn't work out. You have to multiply the fraction or the decimal. In this case, the decimal, because it's the easier way to go. So the probability 0.43 times the probability 0.22 would be 0.0946, or again the 9.5% chance of winning both games. All right, the next one, again, they tell you they're independent. Suppose we know that event A and event B are independent. If the probability of A is 0.42, probability of B is 0.18, find the probability of A or B. So remember, probability of A or the probability of B is the probability of A plus the probability of B minus the and. Right? That was the formula we had in 5.1. This is where we're going to use the fact that they're independent. Right? The probability of A was 0.42 plus the probability of B was 0.18. When we find the and statement, we multiply. It's the probability of A times the probability of B. So we take our 0.42 times our 0.18. And we get, so I'm going to simplify. This comes out to 0.6 minus 0.0756. And so the probability is 0.5244. Again, you cannot straight up add. You always have to check if there's an overlap. Alright, independence just means that when we find the and statement, it's the multiplication of A and B. Alright, it is known that 12% of the population is left-handed. Complete the following sentence, give your answer as a decimal, round your final answer to 4 decimal places. Alright. If 2 people are randomly selected, the probability that both of them are left-handed. If we're just randomly picking 2 people, these are independent events. If a person is left-handed, or I think the WebAssign does some probability of having certain blood types, right? Unrelated people, whether they're left-handed or not left-handed, again, and even then, there's not even sure there's genetics involved. It's just random. And so it's independent. If one person is left-handed, it has no effect on whether another person is left-handed. So they're independent events. So the probability that the first person is left-handed and the probability the second person is left-handed, well, it's just the chance the first person is, which is 12%, times the chance the second person is, which is another 12%, and 0.144. So again, the probability is pretty low of randomly picking 2 people that are left-handed. So if I go out into the street and I randomly select 2 people, the chance of finding 2 left-handers is less than 2%. If 2 people are randomly selected, find the probability that neither of them is left-handed. So, probability that they are not left-handed. First, I'm going to find that, and then I'm going to do my 2 people selection. Alright, probability they're not left-handed is 1 minus the probability that you're left-handed. So, if 12%, 1 minus 0.1... Actually, I said right as a decimal, that was the answer. Alright, 0.12, and so the probability that you're not left-handed is 88. 88% of the population would be not left-handed. Alright, 12% are, 88% are. So what's the chance if I go out in the street and pick 2 people, they're not left-handed. So not left-handed, person 1, and not left-handed, the second person. Alright, well, 88% chance the first person is not left-handed, and an 88% chance the second person is not left-handed. Comes out 0.7744. Again, if I'm 4 decimal places, so better odds, right? If you go out into the street and randomly select 2 people, you have about a 77% chance of picking 2 people that are right-handed, because they're a lot more common than left-handed. Alright, I'm going to stop there. The last thing from notes is just I've mixed together some examples that are similar to the homework, so that's what I'm going to wrap it up with the last video.